So for this first ionic equation, we need to be able to recognize all of the aqueous compounds that dissolve into ions, and they're shown as separate ions in the equation. So ammonium phosphate is soluble, so it separates into 3 ammonium ions and 1 phosphate ion in solution. Zinc nitrate is also soluble, so it separates into 1 zinc ion and 2 nitrate ions, but we need 3 zinc atoms for the precipitate. We multiply this whole compound by 3, giving us 3Zn2+ and 6NO3-. On the product side, ammonium nitrate is soluble and breaks into NH4+ and NO3- ions. There are 3 each. And finally, zinc phosphate is insoluble, so it remains a solid and does not break into ions. And after balancing that, putting it all together, it will come out to be 6NH4+ plus 2PO4 3- plus 3Zn2+ plus 6NO3-. And on the product side, 6NH4+ plus 6NO3- plus Zn3PO4 or 2S. Now, in order to get our net ionic equation, we need to remove the spectator ions. These are ions that appear on both sides of the reaction and do not change. In this case, the ammonium and nitrate ions are unchanged on both sides, so we can cancel them out. What remains now is the actual chemical change. Phosphate ions reacting with zinc ions to form solid zinc phosphate. So the net ionic equation is 2PO4 3- plus 3Zn2+, which goes into the product Zn3PO4 2S. Now moving into this next question, we need to circle any of the following salts that are soluble in water, but first we need to know the solubility rules to remember when determining if something is soluble. So we know all nitrates are soluble, all alkali metal salts are soluble, all ammonium salts are soluble, most chlorides are soluble, most sulfates are soluble, and most hydroxides are insoluble. So looking into each of these salts, barium sulfate contains the sulfate ion, which is usually soluble. However, barium is one of the few exceptions. Barium sulfate is not soluble in water because it forms a solid precipitate. So barium sulfate is insoluble. For sodium phosphate, sodium is an alkali metal, and all salts containing alkali metals like sodium are always soluble in water. So sodium phosphate is soluble. For silver chloride, chloride is usually soluble. However, when combining it with silver, it becomes an exception. Silver chloride does not dissolve well in water and forms a precipitate. So silver chloride is insoluble. Moving on to potassium hydroxide. Potassium is another alkali metal, and all potassium compounds are soluble, including potassium hydroxide. So potassium hydroxide is soluble. And finally, for copper nitrate, all nitrate compounds are soluble in water, no matter what the metal is. So copper nitrate is soluble. So to summarize each of the soluble salts, it is copper nitrate, potassium hydroxide, and sodium phosphate. All right, so moving on to this next question where we're showing how the cations and anions would swap in a double displacement reaction. So first we need to identify the cations and anions. And for silver nitrate, the cation is silver ion and the anion is nitrate ion. And for barium chloride, the cation is the barium ion and the anion is the chloride ion. So essentially, we're swapping the cations and anions in a double displacement reaction. The positive ions switch places. So Ag will pair with Cl- forming AgCl, and Ba2+ will pair with NO3- forming BaNO3 Now, after we've done this, we need to decide which product is soluble and which forms a solid precipitate. So for AgCl, it is insoluble in water because it forms a solid precipitate. So we write it as AgClS. And for BaNO3, it is soluble since all nitrates NO3- are always soluble. So we write it as BaNO3 And here I've written the final reaction. Okay, so moving into this next question, we are given an unbalanced reaction, and now we have to interpret each part of this unbalanced reaction. So CH3OH has 1 carbon, 4 hydrogen, and 1 oxygen, and CO2 has 1 carbon and 2 oxygen, and H2O has 2 hydrogen and 1 oxygen. And looking at the reactants, for 2 molecules or 2 moles of liquid methanol react with 3 molecules or 3 moles of gaseous oxygen. And the products are also 2 molecules or 2 moles of gaseous carbon dioxide and 4 molecules of gaseous water. And here I've included the balanced equation. So for mole-to-mole conversions, in a balanced equation, the coefficients represent mole ratios between reactants and products. So essentially, you can write conversions between any 2 substances in an equation, and there are 6 combinations of pairs, each with a ratio in this case. So from reactant to reactant, we have 2 moles CH3OH to 3 mole O2, and vice versa. And from reactant to product, we have 2 mole CH3OH to 2 mole CO2, and then 2 mole CH3OH to 4 mole H2O. And for 4, we have 3 mole O2, 2 mole CO2, and then 3 mole O2 to 4 mole H2O. And finally, for product to product, we have 2 mole CO2 to 4 mole H2O. And everything that I just listed can also be done and vice versa. So now moving on to the next question concerning dimensional analysis, we need to convert 3.56 moles of CH3OH to number of moles of oxygen required. So first we need to write a balanced equation mole ratio for this. And essentially I wrote 2 mole CH3OH to 3 mole O2. So for every 2 moles of CH3OH, you need 3 molecules of oxygen. So to set up the dimensional analysis, we use the 3.56 moles of CH3OH and we multiply that by the mole ratio, which is 3 mole O2 over 2 mole CH3OH. This ends up coming out to be 5.34 mole of oxygen. So our final answer is 3.56 moles of CH3OH requires 5.34 moles of oxygen to completely react. Now for this next question, we need to calculate the number of moles of water formed when 15 moles of oxygen completely react. So first I have to create a balanced equation for this. And after writing said equation, from this equation I can see that there are 3 moles of oxygen produce 4 moles of water. Now to find out how many moles of water form when 15 moles of oxygen react, we multiply the given amount of oxygen by the mole ratio of water to oxygen. So we multiply 15 moles of oxygen by 4 moles of water and 3 moles of oxygen. And this comes out to be 20 moles of water. This means that when 15 moles of oxygen fully react with methanol, 20 moles of water are produced as a result. So now moving on to limiting reactants. Based on the above equation, if 93.4% yield of C6H8Br4 is obtained, calculate the actual yield produced when 15 grams of C6H12 are reacted with 95 grams of Br2. So first we need to balance the equation. The product has 4 bromines, so we likely need 2 Br2 molecules. So here I've written the balanced equation, and this is balanced because carbon has 6 on both sides, hydrogen has 12 on the left, 8 on the product, due to some H being lost. And finally for bromine, 2 times 2 equals 4 on the left, and then 4 on the right. So to calculate the molar masses, we need to calculate the molar masses of 6 carbon and 12 hydrogen. So carbon has 12.01 grams to moles just for a single carbon. And so we need to multiply that by 6, and that comes out to be 72.06 grams to moles. And for hydrogen, its molar mass is 1.008 grams to moles, and we need to times that by 12, which comes out to be 12.10 grams to moles. So adding those two totals together, that comes out to be 84.16 grams to moles. For Br2, bromine equals 79.90 grams to moles, and since there are 2 of these, we need to multiply it by 2, and that comes out to be 159.80 grams to moles. And for C6H8Br4, carbon has 12.01, and since there's 6, we need to multiply by 6. That comes out to be 72.06. Hydrogen has 8, so that is 1.008 times 8, and that comes out to be 8.06. And bromine has 4, so we do 79.90 times 4, which comes out to be 319.60. And we add those all together, and that comes out to be 399.72 grams to moles. So now we need to convert the given masses in the equation to moles. So the moles of C6H12, for that equation, we do 15.0 grams as we've been given over 84.16 grams to moles, which calculates out to be 0.178 moles. And for moles of Br2, we are given 95 grams, so we put 95 grams over 159.80 grams to moles, and that comes out to be 0.594 moles. Now, in order to determine the limiting reactant from the balanced equation, we see that 1 mole of C6H12 reacts with 2 moles of Br2. So from that, we need to calculate how much Br2 is needed to react with 0.178 mole of C6H12. And in order to do that, we will do 0.178 mole of C6H12 times 2 mole Br2 over mole C6H12, which comes out to be 0.3564 mole Br2. So available Br2 is 0.594 mole, which is more than 0.3564 moles. So C6H12 is the limiting reactant. Now, to calculate the theoretical yield, since C6H12 is limiting, the amount of product formed depends on it. So from the balanced equation, 1 mole of C6H12 produces 1 mole of C6H8Br4. So the moles of the product, 0.178 mole of C6H12 creates 0.178 mole of C6H8Br4. And in order to convert that to grams, we need to multiply the molar mass of C6H8Br4 times 0.178. So that'll be 0.178 mole times 399.72 grams to moles, which comes out to be our theoretical yield, 71.15 grams. Now from this, we can calculate the actual yield using percent yield. So to get percent yield, we do the actual yield over the theoretical yield, and we multiply that by 100. Now we need to rearrange this equation, so it'll be actual yield equals percent yield over 100 times the theoretical yield. So the given percent yield is 93.4%, so we divide that by 100, so it comes out to be 0.934, and to get the actual yield, we multiply that by the theoretical yield, 71.15, so 0.934 times 71.15 equals 66.41 grams being our actual yield.